What's up, guys? Today we're doing a video on rational root theorem. And the rational root theorem does exactly what it says. It finds the rational roots of a polynomial. Now, it doesn't find the actual roots on its own, but what it does find is the possible rational roots. Before we get into it, let's make sure we understand what a root is. I've said before that roots, zeros, and x-intercepts are basically the same thing. They're numbers that if you plug them in for x, you will get 0. Okay? Now remember that a polynomial function always has roots equal to the degree. So this function here in this example is third degree, it's cubic, which means it has 3 roots. There are 3 numbers that I can plug in here and get 0. Now sometimes you may get the same root more than once. So in that case, there may really only be one root, but it will be up to 3 unique roots. Now, there's different kinds of roots. There's real roots, which are real numbers. There's possibly imaginary or complex roots, which involve I. You can also have, within the real roots, there's rational and irrational roots. The only roots that this is going to find are the rational roots, meaning whole numbers or fractions. No radicals, no I, none of that. And again, it's not going to find the roots for you, but it's going to give you a list of all the numbers that could possibly be rational roots, so that if there is a rational root, or more than one, they will be in the list of numbers you get. So let's see how this works. First thing we have to do is understand what P and Q are. The rational root theorem refers to P and Q, and I'm not going to write the actual theorem out. I'm just going to show you how to use it. P is always the last number. It's the constant at the end of the polynomial. So negative 18, that's P. Q is always the leading coefficient, so it's 3. And what we're going to do here is we're going to list out all the possible factors of P and all the possible factors of Q. So what can you divide 18 by? The sign doesn't matter because we're going to start with a plus or minus, because we could divide by the positive or the negative. I could divide 18 by plus or minus 1. I could divide 18 by 2. I could divide it by 3. Can you divide 18 by 4? No. So what would be next? Not 5. You could divide it by 6. It goes in there 3 times. You could divide it by 9. You could divide it by itself, which is 18. And that's it. What numbers can we divide Q by? What can we divide that 3 by? We can divide it by plus or minus 1 or 3, and that's it. So then what we're going to put down here are all the possible combinations of the factors of P divided by the factors of Q. And these are going to be our possible rational roots. So if I were to divide all of these numbers by all of these possible numbers, how many combinations could I come up with? You might say, well, we've got 1, 2, 3, 4, 5, 6 of these and 2 of these. So I could have all of these divided by 1 and all of these divided by 3. So you would think 6 times 2, 12 possible combinations. What you're going to see is that some of those are going to repeat, and we'll see that. So first we're going to say all of these numbers divided by 1, which is just to say themselves. So 1, 2, 3, 6, 9, and 18. Those are possible rational roots. In addition to that, we're going to have all of these numbers divided by 3. So 1/3, okay, 2 over 3, 3 over 3, but 3 over 3 is just 1, and that's already in our list. 6 over 3, well, that's just 2, and that's also in our list. And all of the rest of the numbers are actually in the list already. 9 divided by 3 is 3. 18 divided by 3 is 6. And since those are already included, these are the possible rational roots. Now, these are not all roots. We just said at most this has, or it does have, 3 roots. Now, we don't know, based on this theorem, we don't know how many of those roots are real, how many are imaginary complex. We don't know within the real roots, if there are any, how many are rational or irrational. It could be that there's no rational roots at all. So to find the rational roots, to figure out which one of these are actual roots, we're going to refer to technology. Now we could go through here and plug these in one by one, which how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8. But you got the positive and the negative, so you've really got 16 possible roots here, okay? when you include the positive and the negative versions of them. And I don't know about you, but I don't want to plug 16 different numbers into here looking for things that are 0. When, as it turns out, they may not all 3 be in there. In fact, it could be that none of them are in there. There could be, as far as we know, no rational roots. So we're going to use some technology to help us with that. Okay, so I've pulled up my graphing calculator software, and we're going to go through here and see how to find the actual rational roots from that list that we had before. Now, hopefully you wrote down those numbers because I don't have them on the screen anywhere where we can look. But what we want to do is we're going to go through, look at those numbers. They were 1, 2, 3, 6, 9, 18, 1/3, and 2/3. Now, to do this, we're going to go to y equals and type that equation in. We're going to put in that polynomial. And I've already got it typed in here to kind of save some time. But you type that polynomial into y1. And instead of graphing it, we're actually going to hit second graph for the table. Now the table usually starts at 0 and it'll scroll up and it'll go up and down one at a time from there. And what's happening is these are the x values that are being plugged in to the function, and the y values, which you get out, are over here. So let's say you want to plug 0 into that function, you'd get out a -18. If you plug in a 1, you'll get a 0. Well, remember, we were looking for zeros. We wanted to see when we knew there's up to 3 of them. And as it turns out, I see -3, -2, and 1. They all give me 0 as an output, meaning these are the zeros of the function. And recall that 1, -2, and -3 were all in my list of possible rational roots. So you might be thinking, well, why did we even have to do the rational root theorem if we could have just come to the table and seen the 3 roots right here? Well, the problem is they don't always happen to be whole numbers like this. What if one of the roots was actually 1/2? How would we have found that? Or even worse, what if they were not even real numbers, then, or not even rational numbers? We wouldn't have seen that. So we'll talk about that in a minute. But what about if they were a half? How would you find that? You got to set up the table. And if you're using the small multi-view calculators, you have to do this a little bit differently. But in both cases, you can set up how the table goes through the x coordinates. So instead of counting by ones, you can make it count by something else, or you can even make it where you just type something in and it will plug it in for you. So I'll show you both of those right now. On this calculator, you hit second and you go to window where it says table set on the top. Table start is going to be where you start the table at. Usually it's 0, -3 is fine. It's just because I scrolled up a little bit. Delta table, that's a triangle called delta. Delta table means what is the table changing by each time. This is what's telling the calculator to count by ones. In my example, well, the numbers we had the fractions 1/3 and 2/3. So what you could do is change this, instead of a 1, change that to 1/3. You can just say 1 divided by 3. And it's probably not the best thing to do here, but you could do this, 1 divided by 3. And what this is going to do is, instead of counting 1, 2, 3, 4, it's going to count in thirds, which will allow us to see those numbers in between the whole numbers. I'll be able to see these thirds. And if you had, let's say, thirds and halves, then you'd probably have to count in a common denominator like 1/6 so that you could see all of them. Let's go back to the table and see how that looks. So now you see it's counting in 0.333 repeating increments, which means it's counting in 1/3. Now, we didn't really need it on this problem. We saw all the roots here, but if they were somewhere like 1/2 or -1/2, I'm sorry, 1/3 or -1/3. So like that was one of the potential roots, and this was another potential root. We would be able to see that on here, okay? Another option, and probably a better option for when you have fractions, is to go ahead and keep it in the whole numbers. Sorry, wrong way, table set. Go ahead and keep it in the whole numbers. I'm gonna set this back to 0. Set this back to 1. And go through, check the whole numbers first, and if they're not there, then rather than counting in fractions, we can actually just plug in fractions. And so where it says independent auto, that means it's automatically listing those x coordinates. We can put it to ask. And what this does is it's going to give you a blank. When we go back to the table, x is blank, which means y is blank too. And let's say I want to look at 1/3. I can just type 1 divided by 3 and press enter, and it will plug that in for me and tell me what you get. I can even do -1/3. I can type in whichever numbers I want to. And what was one of the roots was 1, I believe, right? So let's type in 1, and you can see it is 0. I think the other one was it was -2. And there's another one. I think -3 was the other one. You can see there they are. So you can type in manually what you want. Now, if you've got a ton of roots, this is not going to be the fastest way to do it, but this could be a good way to get at those fractions, which are in between the numbers that you want to look up. Of course, you could always just plug these in by hand, and that would work as well. Okay, so let's look at a different example. Okay, so now we have a different example, and this one is going to work out a little bit differently. So let's see how it works out, and try to follow along and see if you can get the right answer. So P is going to be -6. Q is going to be 1. So what are all the factors of 6, plus or minus 6? We're going to say plus or minus 1, 2, 3, and 6. Those are all the numbers we can divide 6 by. For this one, all we got to do is say plus or minus 1, which means all the possible combinations of P divided by Q are really just the same numbers as P. So plus or minus 1, 2, 3, 6. Which means how many possible rational roots do we have? 1, 2, 3, 4 times 2, because it's the positive and the negative. So that means there's 8 possible rational roots. So now we're going to go to the calculator and we're going to see how many of these are actual roots. All right, so we're going back to the calculator, and I've already typed in my y equals. I already typed in the polynomial. And so let's make sure our table setting looks good. I'll start it at 0. Count by 1. We can keep it on auto. We didn't have any possible rational roots, which were fractions. None of them were fractions. They were all whole numbers. So we're going to check the table. Second table. And I can see from 0 to 6 right here, and none of them give me 0, which means none of those positive potential rational roots, none of the possible rational roots that were positive give me 0. So it's not looking good so far. Let's go into the negatives and see. Okay, there's 1. So -3 is 1. And as I go up, there's no other ones. So this could mean a couple things. Maybe that 3 is a root more than once. But either way you look at it, it looks like there's going to be some roots which are not rational roots. Now there could be complex roots, so imaginary numbers. And if that's the case, they always come in pairs. So there would be 2 of them. And they could be irrational roots, which means they would have a radical. So it's probably going to be one of those 2 cases. The 2 that we're missing, we know there's 3 roots. The 2 that we're missing are either going to be irrational or they're going to be imaginary complex roots. So we'll see. So next I'm going to show you how to find those other roots that we're missing. Okay, so let's recap what we have so far. We took this polynomial, we found a list of all the possible rational roots, and as we looked in the table, only one of these was actually a root, only the -3. So that means since we know there's 3 roots, because it's degree 3, there has to be 3 roots of some type, and it looks like only one of them is a rational root, we need a method to go and find out what the other 2 roots are. So 3 roots. We found the root x equals -3 in the table. Now, what we're going to have to do next is going to involve your favorite thing and mine, synthetic division. Now, why is that? What you need to understand is that if x equals -3, if -3 is a root, if that's a 0, then that means there's a factor for this polynomial, which is, can you figure it out? If -3 is a root, then the factor must be x plus 3. Why is that? Let's come up here for a second. Suppose I had a polynomial, and that's probably not going to be this one, but let's suppose I had a polynomial that I factored like this. I'm just going to make some numbers up. Suppose I had a polynomial that factored like this. Remember that we solved equations by factoring. If you can factor a polynomial like this, then you know what the zeros are, you know what the roots are, or the x-intercepts. They're going to be those things that make these 0. So if I had a polynomial like this, my solutions to this equation, which would be my zeros or my roots, would be -3, -2, and -1, because those are the things that would make those factors equal 0. If I plugged a negative 3 in here, I get 0, and 0 times anything is 0. If I plugged in a negative 2 here, I'd get 0, or if I plugged in a negative 1 here, I'd get 0. And if any one of those are 0, the whole thing is 0. So even if I were to graph this, you would see some type of equation, some type of cubic equation that probably would look something along the lines of this, okay? And you would have 3 x-intercepts. So that's what we're talking about here. There's a lot of ways of looking at the same thing. I'm going back to our problem now. If we know that negative 3 is a root, then that means x plus 3 must be a factor. Okay, so how can we factor out an x plus 3? Because that's really what we want to do. If we can factor an x plus 3 out of this, then we can just look at what's left behind and try to solve some other way and find the roots. Which, by the way, with this being a cubic function, if we factor an x out, what's going to be left behind is a quadratic. And we have a lot of methods for solving quadratics that we just reviewed earlier. So let's see how that looks. Okay, so do you remember how we divide polynomials by a linear binomial like this? We do it with synthetic division. So remember we said you would plug in the root of this, which we know is negative 3. So if we know that negative 3 is a root of this polynomial, then I can do synthetic division like this. Negative 3. And then I'm going to look at my factors here, my coefficients here. 1, 3, negative 2, negative 6, making sure I put a 0 if it skips a place, but it doesn't. So 1, 3, negative 2, negative 6. Draw your line. Bring down the 1. 1 times negative 3 is negative 3. That makes 0. 0 times negative 3 is 0. Those add up to make negative 2. Negative 2 times negative 3 is 6. And those combine to make 0. So we had a remainder of 0. Or remember another way of thinking about this, as if it was synthetic substitution. By plugging a negative 3 in here, what we get at the end is what we should get if you were to plug this into that polynomial. And if you want to, you could pause the video right now and plug that negative 3 in here. Everywhere you see an x, plug in a negative 3, and you will see that you get 0 as your answer. So that, again, reminds us that negative 3 is a root. We should have expected to get a 0 here. If we know it's a root, then we should get 0. But at this point, we're not interested in the fact that this is 0. We already knew it would be 0 because it was a root. What we're interested in is this part that's left over. So what would this be? Since we started at x to the third, this will start at x squared. There's no x's, and then we have a minus 2. X squared minus 2 is what's left. And what did we just do? We just factored out x plus 3. So I'm going to bring that down. So this is actually our polynomial up here factored. By dividing out that x plus 3, it's like we factored it out of the polynomial, and this is what was left. If you multiply these back together, you will get this polynomial. And if you have to, go ahead and pause the video and verify that. Multiply this and this. We know how to multiply binomials, and you'll see that you do actually get this polynomial. So we have actually factored it. Now again, if I were to set this equal to 0, which is really what we're talking about here. In fact, we should probably have an equal 0 up here. And I want to solve this again. We already know one of the roots is negative 3. I could put a negative 3 right here and get 0. The question now is, what would have to go here to get 0? Well, sometimes you might have to use the quadratic formula. You might be able to factor and solve if you're lucky. In this case, we don't need the quadratic formula. We can actually solve this one by taking square roots. So as usual, you can set this part equal to 0. So I can say x squared minus 2 equals 0. Sorry. Yeah, x squared minus 2 equals 0. Add 2 to both sides. Take the square root on both sides. And I get plus or minus the square root of 2. How many solutions is that? That's positive square root of 2 and negative square root of 2. Well, that's 2 solutions. And we already know what one of them is. One of the roots is negative 3. So now we have another 2 solutions. So all the total solutions we now know, the solutions are x equals negative 3, square root of 2, and the negative square root of 2. Those are the 3 roots for the polynomial. And if you just want to write these as plus or minus the square root of 2, I'm fine with that. But I just wanted to highlight we do have 3 actual roots. So what did we do? We found the list of possible rational roots. It was these. We looked in the calculator for all of these and found that only one of those, only -3, was actually a root. And even though we didn't know what the other two were, we used synthetic substitution or synthetic division, whichever way you want to think about it, to factor out the factor that contains that root. We factored out the x plus 3 that would contain the -3 root. By doing that, it left behind something which we could then solve to find the remaining roots. Now, this brings up a couple questions. What would happen if, when we pulled this out, we were left with something that was other than a quadratic? Well, in that case, at this point, we don't have much we can do with that. We didn't talk too much about factoring things larger than quadratics. So most of the problems we're going to give you, in fact, it should be all of the problems that I give you, you're going to have, even if this is not a quadratic, you're going to be able to find enough roots this way so that what's left at the end will be, at worst, a quadratic, which you can then solve. Okay, so now all there is to do is just do some more practice. I know it seems like a lot. It looks like a lot of writing for one problem, but honestly, you don't need to write this much every single time. A lot of this is just notes. So good luck and keep practicing.